clustering, because the major difference between clustering and classification is that clustering, we do not know the object identities and observation identity are unknown. Okay? By the way, in clustering, you call everything the form cluster, we call them objects, because you can also use a clustering technique on variables rather than on observation. So that's why I call object identity. So the identity of objects are unknown. So basically, it's unsupervised learning and classification where the membership of or the identity of the objects are unknown. So it's different. So basic types of algorithm, hierarchical partitioning, and other types of things. Okay. And we already mentioned the hierarchical clustering last time. Did I sort of go through this quickly? Let's just use the software to do that. So anyway, just there are different kind of algorithms implemented, and of course that depends on type of distance measures you are talking about. The result could be very different. We already talked about this agglomerative hierarchical methods, and R has this default method called H-class, which is hierarchical cluster. It's bottom up. Okay? And cluster package has also a agglomerative method as well. Okay? We'll talk about that. Which cluster uses a very different name. It's called AGNES. It's called agglomerative nesting. Very different name for that. In R, in the standard distribution in the stats package, we have a function called H-class for hierarchical cluster. Okay? So we will see example anyway. And we talked about this divisive cluster method already. And we talked about this single linkage or minimum linkage. It's going to join the two clusters using the minimum distance, okay, among the minimum distance among all the distances and the pairs of objects in these two clusters coming from two clusters. Complete maximum distance and average linkage, average distance, and there are some other method as well. They are all methods using basically minimize the sum square. Okay? Try to minimize within some square. And now this idea is try to make cluster as compact as possible, like complete linkage is that tendency to come up with a tighter cluster. And in general, single linkage sometimes will end up with very loose clusters. The Walsh method, and there are centroid method, and there are other methods as well. We look at that in our example. Talk about that. And partitioning method. Start with the K group centers. Okay. This is basically a common tactic. Okay. This K group centers, and of course the idea how to come up with centers depends on algorithm. Okay? Some algorithm call for just centroid. Centroid means the average coordinates of object within clusters. And some will just start with the random centers and then do this. Okay, do this cluster. Ouch. Okay, and assign object to closest centers. Okay, and then you update the new center. Right after this new cluster form, you update the center. Okay. And we assign objects until convergence. Okay. This reassignment is very common in like this partitioning method. Okay. We need to reassign until finally the sense all stabilized, right? Okay. I think there's a particular simulation method called the Nearing simulation method. That would be a good idea to apply to this cluster as well. Simulate the Nearing method. Anyway, and so you reiterate this procedure until no reassignment is needed, then you form final K cluster. Of course, here, as the name suggested, you have to assume like number of clusters to begin with. Okay? And because there's a way to compare whether it's good like 3 cluster versus 4 cluster or 4 versus 5, there's a way to do tests and pseudo F tests as well. Okay? And there's also a method that you can compare the 2 different cluster methods and see which one is better. Of course, you want to call for a final result with a less number of clusters as possible, right? Okay. And also, in general, partitioning method also suggests to start with a different set of starting points. So try different starting points, set of starting points and values of K. Okay. And then finally, you analyze results for cluster structure. Of course, remember the final result, this is more or less like very sort of subjective assignment. So, the number of clusters is subjective assignment. And application of clustering, I guess right now we just go. I guess at the moment we talk about this hierarchical method, talk about partitioning method, but this important ingredient in this, all this is distance, how we define distance. Okay. I think I take this opportunity to talk about this couple of distances. I have in note 17. I apologize, I didn't organize this in a nice way, so maybe in the future I need to merge these 2 class notes. This is so-called traditional so-called K-mean cluster. So you want to cluster n object into, say, K homogeneous groups. Okay. So as I mentioned, the number of clusters K has to be specified in advance. Okay. Because this is one K-mean cluster is one of this partitioning method. Okay. And the algorithm will actually randomly choose K data points as the initial seeds. Okay. Well, that's one way. The other alternative, R's implementation allow you to set initial center as some data value. Okay, you can set that. Okay, initial center. Okay. And then for each object, calculate the distance to this object from the C's and assign this object to cluster J if it's closest to the J C. Because this closeness has to be defined, right? So there's some kind of distance maybe. And we compute the mean space named as centroids of the cluster by averaging the respective coordinates. Of course, there's another set of algorithms, similar is partitioning method. Another set of algorithms rather than using the means, the centroid. Use the so-called methods. The reason is that usually you take average coordinates. Okay, that average, the centroid will not be, most likely will not be one of your data object, right? Isn't it? Okay. It's going to be in the middle somewhere. Okay, so others suggest rather than using the centroids, they use the methods. Methods mean that it's one of the n objects, but is most similar to all other objects within that cluster. That's called methods. Okay.
One of the data points itself?
Yes. Okay. Yeah. Methods is one of the data points. Of course, we have to define what's the similarity or dissimilarity measurement. That's the distance. The idea is that so-called method is that within any cluster, you can always measure the pairwise distances, right? Okay. So here, this is one cluster. Okay. So you pick any object within that cluster, you can always calculate the distance, right? And the average distance is one to judge whether a particular object is a methoid or not. So the object that with the minimum average distance will win, will be the methoid. So more like that's the center of that cluster. Okay? So that's an ideal so-called methods. I don't know what's that stand for. Median, something like that. Is it median object? Something like that. I'm not sure where it comes from. Okay. So K-mean cluster based using the means. That's why the name. Okay. And cluster has this implementation called PAM. Okay. PAM is a partitioning around methods. That's the name. We're going to see that. And so here, basically, we compute the means of the clusters by averaging the respective coordinates, and we compute distance to the centroids from each object, and we assign the object to its proper cluster. And when by doing this, probably one object will be closer to other cluster rather than the current assigned. So you have to swap. You have to move that object from current cluster to that supposedly other cluster that is nearer to the center. So actually, this is like K-mean cluster. The idea is all very similar, except that the way how we calculate the center. Right? The K-mean is used as centroids, the mean. That's why it's called K-mean. Now here, let's look at some distance measure. Probably the most commonly used would be the Euclidean distance, right? Okay. Of course, you understand the idea of Euclidean distance. You treat every coordinate as of equal importance, right? Otherwise, you cannot do sum of squares, isn't it? Okay? When you do sum of square, so x1 minus x2 squared plus y1 minus y2 squared. When you add them up, the sum of square, you basically assume that they are same units, right? In a sense. Right? So if you think that all the different coordinates are of equal importance, then Euclidean distance is right. So there are two major classes of distance measure, Euclidean distances, so maybe using some kind of transformation, okay, and after that use Euclidean. So either Euclidean on the non-transform data or Euclidean on the transform data. Okay, so that's a regular Euclidean distance. The idea, basic idea of Euclidean distance, well, let's look at the next slide, not this one, okay. And there's a non-Euclidean distance. The difference between these two types of measure is that Euclidean distance calls for the location, right? Just the Euclidean spaces has some number of real value dimensions and dense objects, and basically there's a notion of average of two objects. Okay? So you look at the location within that cluster. And non-Euclidean basically not looking at the location, but rather the property of objects. So that's a major difference. So Euclidean distance is based on location, and non-Euclidean distance is based on properties of object, okay, but not their location in space. Okay. So that's a major difference between these two types of distances. Okay. I guess this is a quick review of linear algebra, isn't it? Okay. Or mathematics. Is this in finite maths or linear algebra? Metric system. We talk about metric system or distance, right? Okay. What kind of system uses to measure the distance between objects? Okay. The distance measures d is a function from pairs of objects, so that okay, the distance of an object to itself, that's zero distance. This is the properties of that. And of course, for distinct object, okay, the distance must be positive. Otherwise, if you allow the possibility of having two distinct objects but with a distance, the matrix of zero, that's not really a distance. That's called semi-distance. A semi-metric system. But here we do require, so for distinct objects, the distance is strictly positive. And this is the first one is referred to this is symmetry, right? Isn't it? Okay. Distance from x to y is the same as distance from y to x. Symmetry property. And this triangle inequality is supposed to hold, right? So we can go through this quickly. Okay. We understand our usual Euclidean distance that satisfies these conditions. Of course, usual distance is this L2 norm. Okay. So you just distance square root of the sum of square differences in each dimension. Okay. Either this is from the original, you apply Euclidean distance from on the original data set. Of course, where you actually assume that all the variables are of equal importance, right? Usually they are compatible, same scale. Okay, so we can do that. Otherwise, you probably do some kind of transformation before you apply Euclidean distance, like the standardization is one, right? Standardizing variables, if variables are not really compatible with very different units, you standardize variable, then you can apply Euclidean distance. So L2 norm, this is our usual distance, sum of square difference in all coordinates, taken square, right? So it makes it our Euclidean distance. L1 norm is the Manhattan distance, or there's another name, or city block distance, or they have different names for that. Okay, and that's what is called in R. Lowercase, the Manhattan distance is L1 norm. Okay? It's the sum of the unsigned differences in each dimension. So basically, we know that, right? Isn't it? Okay. So distance between x, y, according to this city block differences of Manhattan distance, this is sum. Because assume these are all vector, right? Okay. This would be sum of xi minus yi. Okay. Suppose you have p dimension, okay. Okay. And take in, suppose to take average, right? 1 over p. Okay, and L, this is infinite norm, basically maximum of unsigned differences. Okay. So here, that one is maximum of this, right? Maximums of this. Okay. So in any way, this all depends on the location in the space, right? That depends how you calculate this. Okay. All these two norms, the L1 norm and L2 norms are special case of Minkowski distances. I guess for my class norm, I linked to the class norm in 561, so you can take a look at that. Okay. I try not to get into detail. Okay, so there's other distance measured. These are examples of Euclidean distances, okay? Because it depends on the location, right? You look at the location differences. Okay? Here, there are some examples of the non-Euclidean distances. Okay? I don't know how to pronounce this. This is supposed to be a French name. I think anyone? It's good at French. Jacquard. Okay. Well, anyway, well here this is this distance. Basically, this is for set. Okay, applying for set. You have in the set theory here, distance between two sets basically mean that the proportions of unique elements in A and unique elements in B combined, right? Isn't it? So basically that's the idea, right? Because here this is number of common elements in A and B, right? And then here this is total common elements. So 1 minus the basic. That's how they differ. So this is a proportion of unique elements in A and unique elements in B combined. So that's when we do this clustering, another way to do cluster instead of using distance, you can use a similarity. Because you define this distance this way. Okay. You can always define similarities through difference. Okay. Okay, distances, but not the other way around. Not necessarily. Okay. Well, this we have this one. You can define. Of course, a quick way to look at similarity. Well, this could be a similarity measure. Okay. And usually, similarity measure would have the maximum value of one that's well, in a sense, you say two objects are completely. We don't use the words identical, but this more similar. Okay. Would be 1. Okay? And edit distance is basically a number of inserts and deletes to change one string into another. This is also used. Actually, this idea comes from this. What was that? From information theory, they have this Hamming distance. Okay. Very similar to Hamming distance. Okay. It's a number of delete you make, or the changes you need to make to the graph to make them two graphs to be identical. So that's called, in a sense, Hamming distance or edit distance. Now here we talk about strings. Okay, we'll look at example later. And cosine distance, the angle between vectors from the origin to the object in question. So this one is probably easy, right? Okay. Here, this is an example of this. This is your car distance. Okay. So here we have two sets, right? In a sense, we have two strings here. Okay. So let's say we have two sequences, 1, 1, 0, 1, 1, and then the other one here. One is presence of certain certain event, okay, or certain straits, we like to call it, and then 0 is the absence of that such a strait. The distance between P1 and P2 is this, right? You put them side by side, you can see that, okay? Put it side by side. These two sequences are different in only two locations, right? Isn't it? Right? In the second and third location, right? Okay. So it's 2 out of 5. So there's a distance between these two sequences. Okay. And an equivalent definition of edit distance can be done by this. It's basically you can. You don't have to actually put them side by side and see what is the edit distance number of deletes and edits, okay, that you need to, or insert needed to make one string into the other. Okay. The other way is look at this. You look at the longest common subsequence and count number, okay, of elements in that sequence. And then here, this is the formula to calculate the distance. Let's look at example. Now, let's say you have these two sequences, or two words, whatever that is, okay? To change, let's say to change from x to y or y to x, for example, let's say x to y. This has to be distant, right? Change from x to y or from y to x will be identical. Okay? How can you do that? If we just use the definition, right? To change this sequence into B, C, D, G, H, first you need to remove this one, right? Delete A, right? And after deleting A, then you need to do insert two characters here, G and H. So the edit distance is 3 based on that. Okay. So number of deletes or inserts is 3 in this case. Okay. So use the first definition, return x into y by deleting A, okay, then inserting G and H. Okay. After D, then you get this. So that's edit distance of 3. Okay. If you use the second definition, okay, use the longest common sequence definition. Okay. Both sequences contain B, C, D, and E. Right? You have B, C, D, and E as well. Right? So longest common sequence. Okay. When they say longest common sequence, they do not have to be consecutive. You know, that's what is contained from left to right. Okay. So here, the longest common sequence will be B, C, D, E. So length 4. Okay. So 2 times length 4 will be subtracted from 5 and 6 each. Right. So 5 plus 6. These are 3. Does that make sense? Actually, if you just look at the distance of this, not really completely helpful. The distance that would be helpful to us would be the one I'm going to talk about. Okay, this is called the Goer's distance. I think it's pronounced Goer. or dollar. Anyway, goals distance basically, it can come with all kinds of combinations of variables that you have. Okay? Actually, that's really suitable for our task, right? You have data set that come with different measurements, right? And the properties of this measurement could be very different. Some categorical, some numerical. Okay? Even categorical, you have the ordinal data, you have nominal data. Even binary data, there's something very different called symmetric binary data or asymmetric binary data. So let's look at that. Okay. First, look at the binary variables. Before you understand this, the distances, this goal is distance. Let's look at so-called like a different type of variables we have. Okay. So binary variables, they are coded as 0 and 1. Okay. Symmetric binary variable is that there's no preference as which label you assign 0, which label assign 1. You can reverse it; it doesn't make any difference. Okay. That's called symmetric binary variable. Okay. So no preference for which outcome should be coded as 0. Or 1. So for example, you say coding the male equals 0, female equal 1 is of no difference than say coding say female 0, male equal 1. So that's a symmetric. This is called symmetric binary variable. Okay. So this, of course, your binary means that dichotomous variable means you have two possible outcomes. So symmetrical, asymmetrical. On the other hand, okay. Well, of course, this is quite applicable in prediction. There are many situations that sort of arise on this type of asymmetrical. Okay? But in a sense, I would consider this asymmetrical binary as some kind of ordinal data, isn't it? You may, right? Okay. If you code 1, that means that one is, if the absence of that means is of more serious consequence than the other label, right? Can we call this as an ordinal binary data in a sense? Okay. The definition is like this: the outcomes of a binary variable are not equally important. Okay. So, for example, the presence or absence of some very relative event, okay, or attributes, okay, such as like colorblind or not, okay, for human being. Okay. So, let's say two people who are colorblind have something in common, other than their being colorblind. Okay. And on the other hand, there's much so, right? People who are not colorblind do not have anything in common, or very little in common, right? So this kind of matchup would be less important than the other matchup. With 1-1 matchup, that's more important. That's more serious consequence. There would be more similar. Okay, so basically, in general, other than not, or in this case, usually we code 0 as the absence of such a rare attribute, okay, and 1 would be the presence of such attributes. Okay? You want to code the other way around. So in a sense, this is the ordinal data, right? You may say so, right? Okay. Of course, I want to raise this up because later on when you define this so-called goal distance, okay, and this is where and role in that. Okay. One of the critical roles in calculating the goal distance. Okay, so this is like for symmetrical types of binary variables or asymmetrical type of binary variable. Example like that. Because categorical variable is simply just called as say 1 to k of the k distinct values. It's just regular nominal variables will be just coded as that. And ordinal variables still use the first k integers to code that. But remember, ordinal variables, we understand that. Okay, because here I'm not put 1, 2, 3. This is not in the sense of the real number. This is like coded level, right? Okay. In this order, coded level 1 is the sort of smallest one. Coded level 2, the second smallest, and so in order. Still using this, so we also use k integers like that. Okay. For the I think there's a type of distinct value. Sorry about that. I think we'll change that. Okay, this is how goal distance was defined. And actually, it's defined. So suppose now we are looking at between objects I and object J. Okay. This for the time being to consider objects are observations, okay, and then we have variables, right, in the columns. Okay. So the distance or a distance between two objects or two observations I and J in the p variable data set. Okay. So here these p variables can be of any combination, right? Okay. And actually, look at that here. This is some kind of distance measure between object I and object J that we have in variable k. So in a sense, you look at that. This is actually the weighted average distances, right? Let's say, suppose here dijk, this is the amount of this contribution to the total distance that we have in variable k. So basically, this is actually weighted average of that. Okay? And then the weights are given by this. Okay? I will explain further. At the moment, let's just look at individual elements in this distance. Okay? First of all, WK. This is weight. This is overall weight for a particular variable. Okay? So here, WK is the weight for variable k, which gives the weight of importance of the variable. Because by default, it will set average weights of all the variables. Suppose the variables play equally important role. You know, we can use a weight of 1, right? Okay. So basically, the result is that just if this is 1, this is like a regular average distance, okay, in a sense. Okay? Of course, if you remember, this is very sort of subjective assignment. That if you find that some variable you think is play a more important role than others, then you probably want to use unequal weights. Okay? We assign unequal weights to the variable. Okay? You can do that. Okay? And then this delta ijk, basically this is indicator variables. It has value either 0 or 1. Okay? This is indicator in very comparison observation in I and J in variable k. So for the time being, let's just look at particular variable k, delta ij k basically giving that whether it's a very in comparison and you have value of 1. Okay. So text either 0 in very comparison when missing value or values occur. If this in this variable k, one of these two objects has this one of these two objects has a missing value, then this is invalid comparison. Because you don't have information for at least one variable, right? It doesn't give a valid comparison. So you have value of 0. If both are non-missing, okay, for both both I and J are non-missing in variable k, then you assign this delta ijk 1. So sort of indicator. Okay? And also in addition, or in a sense, I do not want to call this invariant comparison, so I set it aside. Okay? In addition, if the variable is a symmetric binary, that's why I didn't mention that first. Okay? If it is a symmetric binary, then delta ijk will set to 0. Okay? If both observations are 0 and 1 otherwise. Because usually both are 0 means the absence of such value. You should probably doesn't play any important role in that. So we just set that as 0. So other than that, okay. So here delta ijk has a value of 0, 1. So in a sense that if you look at this formula, in a sense you kind of take care of this. You kind of remove all invariant comparison, and also remove this type of no significant comparison. Whatever is remain, that will be you have the weighted average over this type of variable, right? Isn't it? Okay. Because some of this term is going to be 0 anyway, right? So basically you only sum for over all the variable k where this delta ijk not equal 0, right? Yeah, they're 1. So basically weighted average will remain. Okay, so that's the term. And then how about dijk? This is most important part. Actually, the formula I list out here, this is the implementation in R. This is not the original goal distance. This is modified. Original distance assume that there is no missing value. Okay, although it takes care of this less important variable like 0, 0 pair for asymmetrical variable. Right? Okay. It doesn't take care of the missing variable. Okay. But R, this implementation in R has this additional twist here because it can take care of the missing variable. Okay? So with this definition, okay? And here this dijk is a contribution in distance, okay? Between of a distance between observations I and j in variable k to the total distance, okay? And it's defined as this, okay? If the observations are in agreement, because at the moment here we already take care of those situations, right? So actually you can define only those for those valid comparison, and for those when you have asymmetrical binary only for those sort of significant comparison. Okay. Of course, observation in agreement, that could be a case that you have in a symmetrical where both are present, then you have agreement, right? The observation in agreement. Then you have distance of 0, okay, between I and j in variable k. Okay? And would have value of 1, distance of 1, otherwise for binary or nominal variable. Okay? If I and j are different, okay, for binary variable or for nominal variable, then we define different distance as 1. Okay? This is badly formatted. The denominator is r. Okay, sorry about that. Okay. For ordinal data or numeric variables, remember I already mentioned how we define ordinal variable, right? We simply just use the integers 1, 2, 3, and so on to k. You pick k level, all the data, right? Ordinal data. Okay. So, and the denominator will be the range of the ordinal numerical variables. Of course, for ordinal variable, the range is simply just number of levels, right? K. And now here, this will be a difference, okay, unsigned difference between these two objects. Suppose now in pair I and j, one is from level 3, the other from level 5, and this is out of 10 levels ordinal data, then the result will be 2 out of 10. So the distance of 0.2. Okay, for that. Okay. So here, this is the definition of that, and then taking the weighted average of this distance, we have this so-called Gower's distance. So this is really convenient, right? This takes care of all types of variables, isn't it? Okay, this definition. And Gower claimed that this was in 1972 paper. Gower claimed that in his original definition, when all variables are numeric, this is the result is equivalent to Euclidean distance. Of course, not directly identical to that. Equivalent to that. Okay. Does that make sense? The last formula here, right? This formula is only used when you have ordinal data or numerical data. So, okay. Of course, in case of ordinal data, the denominator is simply number of labels for all ordinal data. So that's the so-called Gower's distance. Now, with this in mind, then you can do clustering. Okay. Once you define these distances, I want to get into our example today. I already loaded this up, 16.9. Did you get this? I put it online. Okay. Should I talk about your case study file and final project? Sure. Talk about it later. Let's spend a little bit of time here. You already seen that, right? And I have to make a promise, and then I will force myself that I'm going to finish grading your case number 3, case study number 3. You didn't get that back yet, right? So I'm going to do that by this weekend, so you can get it before Thanksgiving holiday. Thanksgiving holiday this year is coming so early, isn't it? Usually we have only 1 week left after Thanksgiving, right? But not this year. We have 2 weeks into that. Okay, now first look at this. This is the protein data obtained from DESO. Of course, I also have an example from 561. I put a link to that, right? So you can look at other example. Okay? Let's just look at this one. Actually, the links to 561, I didn't talk about anything at all about the cluster package, but here I do have an example of cluster package. This data set was from DSO. This is data set and story library. It's in this link. Okay? I think I put a link in that note 16 as well. Okay? And if you click on this list all method here, of course you can data set or stories are organized in different way. One way is this one method. You can see convenient cluster analysis, right? Okay. So you click on the cluster analysis. I have a data set from one of this row. I picked this protein consumption in Europe. They even already have this cluster result, so we can actually compare the result. Okay. So click this protein consumption in Europe story. Okay. Here, this is descriptions about this data set. You see this dendrogram already, right? Put this dendrogram sideways. You already see that. Okay. And you even said this is part of computer linkage cluster analysis. But it didn't say clearly. I showed that. This is done by Euclidean distance on the standardized variables, not the original variable. Okay. And of course, you go to that, you can look at this protein data. Again, it's another web page on that. I don't know why they do not want to separate data set from descriptions. Not really convenient directly, but of course, you can always work around this to get this data set in. Okay. Here, basically, this is about the data set with country name as the first column, and then here, these are the protein consumption over these different types of foods. Okay. Except for country, which is ID, the rest are numeric, right? These are numerics. Okay. So actually, you can do this. In addition to that, I take the freedom of looking at these descriptions, okay, and I add a new variable called geographical location. Okay, and I can see that it's explained right here in this data, the description of story. They have these 6 different locations geographically to do that. Okay, so I also enter this information there. Other than that, here this is how I construct data. Basically, I do copy paste in a sense. You can highlight this. Okay. So you can highlight this entire data set. This is an HTML page, unfortunately. And make sure your cursor goes down to below the one line below the last line of that. Otherwise, you won't get to read last line correctly. Okay. So make sure you highlight it. So highlight this and paste, right? Just copy. All you have to just copy is copy the clipboard. So after that, you can actually, if you copy the clipboard, okay, you can actually read by this. Okay. I already done that. I already saved the results. So that means, well, you can actually retry this anyway. Can I copy? Copy that. I can copy and paste into the clipboard, and then here just run this command. So read the name, and it's explained in the data set. The fields are separated by a single tab characters, okay, and invisible tab characters. Okay. So use a read delim just allow you to read the tab delimited data like this, and it's inserted in clipboard, right? Okay, we copy. You copy that. It's in clipboard. This is just what I want to read that. And header equal to, because I highlight the first row. Okay, first row will be the variable name, right? Except the last column is not the legitimate variable name. I will take care of this automatically with something that I probably don't like. We can change it later. We can change it later. And we notice that the first column basically will be served as ID, right? Variable ID. So simply just say row.names will be first column. Okay. There's another data set, they have this ID on second column. So you just do a copy. namely the cars data set. One of these four is a car data set. The ID is in second column. You can actually do that. Okay. So here, this is our first column. So read this in and look at the names of protein and find that the last column is called. Maybe I should do this. Doesn't matter. We run it again. So here you have this read.lim, okay, and names protein. You can see the last one was changed to this because they have this, not supposed to be variable name in the data set. Last column is like this, right? So that is changed automatically, okay, within R. And I really don't like that, so I changed the name for that column. Okay, so simply you can just do this. So you say names of this protein, the nice column is this name for that. Okay, it's not really important though. Okay. And then I manually add this geographical location into that. Okay. Unfortunately, you have to do that. Okay. Because I sort of try to add new columns here. So add a factor according to this geographical location of the countries. There are total 25 countries here, so I assign an X here. And then basically, there are 5 countries come from first region, and 4 countries from second region, and so on. So here I kind of put this way. I make it easier to read. Okay. Why not let me just do this directly. So, and now here we actually make a label and then assign to geolocation in Y. Let's do everything. So here, this is the final result. Okay. Let's look at the first of 5 countries of that. So here, I add this geographical location later on. I wanted to use that later. So. Now, suppose we use the Euclidean distance for the 9 numeric variable, but we scale them because, well, in a sense, you can argue that these variables are slightly different. Some are protein from vegetables, right, or fruits. Some from animals, right? So, supposedly slightly different property. Okay? So it's nice we standardize first before we take a Euclidean distance. So that's why I do this. H class is the built-in R function to handle hierarchical clustering from bottom up. So this is a agglomerate hierarchical clustering. H class, okay. It requires a distance matrix, okay. And DIST again is a built-in function, okay. Comes with a standard distribution to calculate for data matrix, the data frame, okay. And we calculate the distances. Because when you do Euclidean distance like this, in this case, all variables are numeric, right? Otherwise, we cannot do that. So here I remove the last column. Last column is geographical location, which I'm not going to use in this example right here. Okay. So excluding that last column of geographical location, which is a factor. Okay. And then, so here I've scaled that first. So standardize first. Standardize individual variables using scale function. And then calculate distance measures. You can actually see this is what's going on the distance. Oops, there's another parenthesis like that. Okay. So here, this is distance matrix given by that. Okay, it's a low triangular matrix. You can see that. Okay. So here it gives all the distances, Euclidean distance of the standardized variable. And then you run this H class directly, this hierarchical clustering to this and use a default complete linkage. This is the default linkage. So we have this result stored in this PR H class, or this H class there. So and then we can plot the results. Okay. This is protein consumption in Europe. Okay. We use a computer linkage, and here this distance of scale, that all this protein information. Okay. Okay. Of course, well, this is the final dendrogram result, and you want to see cut into few clusters. Okay. Of course, I didn't spend too much time on studying all other possibility, but I just take that from this web page. Let's say we cluster that into, we put this into 6 clusters, okay, and see how we do that. Okay, the command here, this rect .h class allow you to basically graphically, okay, put the sort of boxes or cages that surround the clusters, with this number of clusters specified there. Okay. The border 2 colors, the border colors 2 to 7 base. That's what I added on myself. Okay, so it's not really important to have that, but actually you can see that. Okay. You can run this. So this rect cluster allows you to do that. So let's run it anyway. Okay. So produce this. Use this rect.h class. Okay. It's going to put this surrounding box there, as you can see here. Right? Okay. Actually, this is sort of properly clustered to this 6 different geographical locations. This is these are all about the Balkans countries, right? Okay. So Balkans, and this is like West Europe, right? More or less. And this is going to be what is that?
Northern.
On this upper part. I kind of try to enhance this graphics by doing this. For this case, it is suitable to add this. I add all the legends of these 6 boxes separately in 2 legend functions anyway, and each one is called for the location. So you really need to do that. Okay. So when you highlight on that, still will allow it to go outside. So you can simply just do that. Maybe this is not the best way. So let's identify that. Okay. And second one right here, another legend box. Okay. You can press here. I do this. I can press it on the other side. Okay. This doesn't go nicely. How about we do this? Much better, right? Okay. So here, this hierarchical clustering of this result, it results into 6 clusters. Okay. That's the final result of that. And actually, at the time we call this the rectangular box of this hierarchical clusters, actually internally it's called for a cut-tree function. Okay. And I also print the result. Here surround this I use to print. Otherwise, when it's a dot cluster, it's only placed that this box is around the dendrogram. Okay. But you can also output this by print this result. Here I surround this with print function. That's why you see this result. There are basically 6 clusters that we form. The first cluster are these Eastern Europe countries, right? Okay. And then here this, how to call it? These countries are Scandinavian. How do you pronounce that? Those countries, right? Yeah, Scandinavian. Yeah, okay, right. Okay. I actually have this result. And then here these are Western Europe countries, and then here Iberian. Was that because that this peninsula is named after that, right? And these are those in the Mediterranean countries. This Balkan. Well, of course, this fit in this data nicely. These are actually all these different 6 geographical locations, even different distances, and you see the common cluster result, right? And that probably give you a better interpretation of the outcomes, right? So if some groups or some some of objects are consistently classed as from one group over different method. That's more like maybe that's a natural group. Here, the next example, I use a goal distance. Actually, probably this is not best data to show. Anyway, in this case, this goal distance or this geographical location basically just dominates everything. I think it's probably for obvious reason. This is nominal data. It's 6 level. Right. So if you use any linkage here, so end up with the same result. It's correctly clusters everything that's from its respective geographical locations. Use a goal distance. Goal distance can be found in the cluster package. I remember I mentioned cluster package come with a standard distribution. They all use this strange name for that. Okay. Oh, okay. I forgot to mention the last comment. I mentioned that actually this rectangles of each cluster is called internally with this cut trees. If you do this cut tree, you end up with the same result. Run this cut tree. You see with that. That's basically the same result as you see. Okay. So here, do a goal distance. You can see that in this folder, you can see there are data sets and there are also methods. Okay, you have this Clara method. Okay, this is clusters for large applications. Okay. I forgot this R stands for, but this is really large applications anyway. Okay, for large data set. And then you have this class for the partitioning method. The objects that are out from this partitioning method. And then you have this DAISY. This is a distance measurements. Measured by default, it's Euclidean distance, and you also have Manhattan distance and the Gauss distance as well. The Gauss distance cannot be found in the original the R distributions. That's why we have to use that. This is DAISY. Diana, this device analysis of cluster. We've seen that already. Okay, and there's something else. Okay, we look at the PEM. This is partition around methods. Okay, so different. They use a very different, very interesting name. Okay. Mona is to apply with all the variables are binary. And there's also Agnes. This Agnes method is a normative for nested analysis. So basically, we're going to use some of this again. But here, I only make use of this cluster, the DAISY function, to calculate the goal distance. Okay. So here, this is a commit to use, and I perform this hierarchical clusters on that. Okay. And I call on this cluster the DAISY function to calculate goal distance. And I include everything, right? Including that geographical location, the last column, okay? And I say standardize is true. So the variables, the numerical variables will be standardized before the calculation. Only numerical. Okay. And let's look at this compute linkage. Let's just do everything. Of course, the colors are different now. The colors that because this different orders of this cluster presentation be different, but still. So I didn't put a legend here. Of course, here still this is probably still with the right order. Maybe we can still do that. Okay. So in a sense, it's correctly clustered that using goal distance even. But in a sense, I would think that this goal distance. The last variable, this geographical location, really dominated in this goal distance. I think maybe you can check whether it's the case. So it just end up with this. Even if you try use other linkage method. So here I only use what was that? Where are we at? Yeah, right. We have this clustering of goals distance. Okay. I only use a complete linkage here. But you can try other linkage. They all end up just end up with the same. All linkage result in the same result. Clustering if 6 clusters were formed from cut tree. Okay. Except that you find something reversal. Okay. Here, actually, I can show example with the reversal. Let me change this to centroid. Let's see the result. And explain the reversal. You see the reversal right here, right here. Okay. See the cluster formed in later supposed to be of a greater distance, right? But this is not the case. You see the reversal here. Because in this case, these clusters are formed first, and then later the frames join to that, but with a shorter distance. Okay? Usually it's not monotone, sort of not a monotone height when they join together. That's called reversal. Reversal is common in like centroid algorithm, centroid linkage or word linkage. Okay. Usually this is less desirable if you have something like this. It's because it's harder to explain. Right? How can this new object join to the existing object with a shorter distance? Okay. It's really hard to explain. But nevertheless, you still end up, if you cut a tree with the 6 clusters, you still end up with like the same kind of cluster. Okay? They are consistent with that, except that of course the order that will be different. Okay? You can try this out with this centroid and maybe other. Okay? I think H class has another method called McCurdy, so they have different linkage method, right? Or different linkage. It's kind of interesting to see that. Now let's look at the divisive analysis clustering. So that's why it stands for. It's called Diana. So they all use this different, different interesting name for different algorithms in this package. So let's say because from this point along, I will use the method from that package, so just load it. Actually, in our case, I already load that package, so I don't need to reload that. This is already loaded. You can actually try that. There's no response, means it's previous loaded. Okay. So here, let's run this directory. So we asked about this divisive analysis clustering of our protein data, excluding that because I want to use the Euclidean distance. I cannot have that there, right? I cannot have this nominal data in there. Okay. So I have protein, say -10, and metric will be Euclidean metrics, and standardization should take place before Euclidean distance was applied. Okay? So that's why we have that. Oh, Diana used a D4. D4 is Manhattan. So, oh no, sorry. Euclidean distance still D4. So okay. So here Euclidean distance is D4 and Manhattan is the only alternative to use this divisive. Okay. So let's run this. When you see that, it tells you to wait to confirm page change because by default there are 2 graphics produced. So here, the graphics window will be active. So you click within, use the left click anyway. Produce a so-called banner plot. Actually, this is they say this is very nice presentations of dendrogram. I don't like it, but anyway, this is another view of dendrogram. Okay. And you can see the dendrogram that okay. The previous graph is Copernicus graph. Well, it's just made of case. I don't really like that. Well, I like it more from this dendrogram, the traditional graphics on that to show the result. And now we can see that. Oh, okay. I forgot. I cannot use hand for this type of object. This diagonal object do not have this hanging there, this hanging parameter, so I should get rid of that. And this is a rect H class that doesn't fit nicely, but as you can see, this grouping, if you can still do the cutting with the 6 clusters. This. It's not exactly consistent with the geographical location, right? That's close enough, isn't it? Okay, so here, according to the protein consumption, say, with 6 clusters, these are the countries grouped together, right? Okay. So using this algorithm. Let me finish this, just the last one. This is this agglomerative nesting algorithm that is implemented in the cluster. Okay, it's called AGNES. See, they all come out with this strange. Just waiting for that. Still, you see this Banner plot. This is another way to present dendrogram. Here is our dendrogram for this result. So we run AGNES on the DAISY. I use all data variables here, including the geographical location and standardized. Okay. I think that kind of clustering is still maintained in this case, right? So more or less, like you can see that you cut this a proper location, you're going to divide into 6 parts according to their geographical location. So still that geographical location information is really dominated. Maybe we should exclude that and then just let the algorithm take care of that. Okay. So here this grid is Italy, okay. It's just by itself, we cut it here, and then here Portugal, this Portugal and Spain, and this Western Europe. So actually this is still correctly, in a sense, correctly clustered. Let me start now. Well, this type of graphics, you add additional so-called this agglomerative coefficient. Okay, one would be the best. I mean, this is how tightly the clusters are formed. Okay, one being the best one, right? Okay, very compact clusters. Okay, so let me